right, in the second video, we're going to talk about broadcasting. So we'll step through an example of broadcasting that you will need for your K-means algorithm in order for it to run efficiently. Most of the time, I'm not worried about readability, but in this particular case, it's pretty important that you get the idea of broadcasting. So I'm going to make sure that your algorithm, I'm going to take off heavily if you don't use this idea. And instead, you try to use two nested for loops, and that just means you didn't sort of pay attention to what's going on in this video. All right, so I'm going to just step you through. I'm not really typing in anything in this video. We're just going to be able to step through and knock it all out. So the broadcasting example that we're going to talk about is one where you're given a set of points, and so these are XY points. So 2, 4 is position 2, 4, and -1, 8, right? So that's 2 points in the Cartesian coordinate system, and two-dimensional points too. And then I got -5, 3, 1, 2, and 6, 9, and I want to find the distance or the squared distance from each one of these points to each one of these points. And so that's the idea. We want to find the distance. Okay, so you can kind of read that. And I claim that if you do this calculation here, so if you do this, you will actually have the answer. So this will give you something that'll solve the answer. If you did this one, if you just did A minus B without doing this reshape business, then it's just going to give you an error. And hopefully we'll see why that gives you an error here in a second. So here are the 2 point or a group of points. So 2, 4, -1, 8, -5, 3. So this just comes from your course guide. You should have seen this before, but I'm going to step you through the example just sort of step by step in order for you to understand. Also understand that this would absolutely work. So the problem with this is it's really, really slow. So these 2 for loops here make this really, really slow. And what we want to do is we want to utilize Python's C code in order to do broadcasting in order to make it very, very quick. All right, so what are we going to do? First thing we're going to do, take this matrix, this two-dimensional NumPy array, and turn it into a 3-dimensional NumPy array by doing a reshape. So we're going to reshape it, and then it's going to look like this. So it's going to have 2, 1, 2. That's what we want it to look like. So that means 2 files, two matrices, 1 row, and 2 columns. Instead of being in 1 matrix or 1 file or 1 table or whatever you want to sort of call this first dimension, I think I'm gonna call it files. I think that makes a lot of sense, because if I had another one behind that'd be the second file and then the third file. But you might hear me call it matrix as well. But instead of having one matrix and then a 2 by 2, I'm going to have 2 files where it's a 1 by 2. So that's all we've done. So I've taken this data and reshaped it to look like this. So the 2, 4 is out front, and the -1 and 8 is the matrix, the 1 by 2 matrix that's behind that one. And then B just stays by itself. And then when we do this subtraction here, we're going to apply broadcast rule number 1. What do we mean by that? Well, read what broadcast rule number 1 states. If 2 arrays differ by the number of dimensions, so again, this is a 3-dimensional NumPy array, this is a 2-dimensional NumPy array. If that's the case, then pad the smaller array. All right, so this one's the smaller one. All right, it might have more data points, but it's the smaller one because it's only 2-dimensional. We're going to pad it on the left with a 1. So this becomes a 1 by 3 by 2. It looks exactly the same, right? So it's a 3-dimensional NumPy array now. It has 1 matrix instead of, well, I shouldn't say instead of, because it is just one. It's still just 1 matrix. So you really haven't done anything other than just put a 1 out here. And this one's a 2 by 1 by 2 still, so it just came down. Didn't do really anything to it. So the next step that we're going to do when we're doing the subtraction, so if you're applying the broadcasting rules, the next thing that's going to happen is it's going to look and say, well, that 2 is not the same as that 1 right there. The shapes have to be the same in order to subtract. In other words, if I have a 2 by 1 by 2, the only way I would be able to subtract that is if I had a 2 by 1 by 2, or if I applied the broadcasting rules. So that means I need to make this 1 be exactly a 2. And the way you do that is you replicate what you have in this matrix. So if the shape of the 2 arrays do not match, the shape meaning the numbers in this So if you go A dot shape, it'll give you 2, 1, 2. If you did B dot shape, it'd give you 1, 3, 2. They don't match. And the way that I stretch it is I replicate. So I kind of give you the red code here that talks about, well, that just means replicate the data to make the sizes, the shapes match. Pad of 1 is all I'm using for this second broadcast rule. The third broadcast rule is if 1 and 2 can't make the array the same size, then raise an error. Okay, so let's keep moving on down here. Now we replicate the data in B in order to make that a 2. That means I'm going to have two files. So I'm going to have, or ranks. Did I say rank? I said files. So I'm going to have 2 files. I'm going to have negative B. So I'm going to have the same exact matrix in the front, and then I'm going to put the same exact matrix in the back. That will give us a 2 there. So 2, 3, 2. This thing is done. And then the A just again comes down. Now the next problem that I run into is there's a 1 here and there's a 3 there. They don't match. So what are we going to do? We're going to replicate the data in A so that we can turn that 1 into a 3. That means I got to have 3 rows. I'm replicating, so that's 1 row of data. And I'm going to have another row of data and another row of data, and it's going to be exactly the same information. So if you come down, you'll see that. So I got 2, 4, negative 1, 8, 2, 4, negative 1, 8, 2, 4, negative 1, 8, right? I replicated it 3 times in order for that to become a 3, which it did. And now the shapes are the same. The 2, 3, 2 matches the 2, 3, 2. We don't have anything else to do in the broadcasting world, and we can just do the subtraction. So go back and you can look. 2 minus a negative 5 is that 7 right there. Negative 1 minus a negative 5 is that 4, and so on and so forth. So the rest of these numbers in here are just looking at subtraction. The thing I do want to point out is if you look at it from the columns perspective, now think about that for a second. What stayed the same in all of these? It was the number of columns. So the number of columns never changed, and that's what you're dealing with as far as, like, that's the view that you want to look at this thing. So what does it mean by a column view? It just means you're sitting on the side looking at this tensor from the side. So what does that mean? Sort of put a line in between all of this data. So the first thing you're going to see is this matrix, and the second thing you're going to see is this matrix. This first matrix represents delta x. The second matrix represents delta y, and that's it, right? So that is how you're going to go about using the information that's in this tensor in order to calculate the squared distances. So you just find we'll see it here in a second when we get to the code in Python. Let's go back up real quick. I think I talked about this. Like, this code would work, and that's exactly what we're looking for, but I want to do it with broadcasting. All right, so let me restart the kernel. Make sure you import NumPy when you do this one. So go ahead and import NumPy. We got a 3.2 and a 2.2, and guess what? Broadcasting rules don't know what to do with this. And if you ran it, it would say, I don't know what to do. Maybe I could. So the problem is it doesn't know whether to copy another column, another row, another whatever, right? So it doesn't know which one of these two to copy to put it down on the bottom. Let's look at the reshape. And so what happens when I reshape this thing? Well, you can see Python, or at least Spider here, gives you sort of a visual what's going on. So I got this row, and this row is behind that row with the 2 columns in each one of them. So it's a 1 row matrix and another 1 row matrix behind it. And then, of course, it doesn't stick, because if I try to do this, it still doesn't work. So I'm going to do this A1. So A1 is equal to that, and then I'm going to let C equal this. Now, when I hit the button here, F9, Python's going to do all the broadcasting rules that we talked about here a second ago. It's going to do it very, very quickly. And we can look at the shape of it. So it's a 2 by 3 by 2, just like we suspected. And then, so 2 files of 3 rows by 2 columns. So the first file is this one, and the second file is this one. All right, so what happens when I do this piece? Remember, we're looking at it from a column perspective, because the columns always stay the same. If I had 3 columns, that would be fine too. That next one would be delta z, so this would be delta x, delta y, delta z. And let's look at what happens, and we get the 55, 41, 41. So we get exactly what we want. I'm basically taking your delta, all of your delta x's and squared them, and then I'm adding that to all your delta y's squared, and we get what we're looking for. So let's look at C. Look at it from a column perspective, and that's what it is. It's that that 2 by 3 matrix that we thought that we were going to get. All right. So what would happen if I went from B to A, right? So you would think that it would look a lot like this thing down here, because it doesn't matter which direction you sort of look at it. However, it does give you a different dimension matrix, right? So that's the rub here, right? So we get that. So B1's equal to that, then D. So let's look at D. Now it looks a little different, but it doesn't change the perspective you're looking at, right? So if you still look at it from a column perspective, this first one's going to be all of your delta x's. The second one's going to, so let's look at what D looks like. Let's bring it up and look at it from a column perspective, and you're still getting a matrix with all your delta x's in it. And then, oops, stay on that one. And then you're getting another matrix behind that one that has all your delta y's in it. So let's recall real quick. So you're always going to be looking at it from the side, and this is that first matrix that you get here, where I put that's the first one you can see, and then that's the second one that you can see. So 7, 4, 1, -2. Let's go back to the last one. 7. Oh, it's minus that, right? Because we subtracted. We went the other way, so that does make sense. And then what would happen if did we do that? Yeah, we did. So this is a 3 by 2 matrix instead of a 2 by 3. And the numbers better be the same because we're squaring them, so it doesn't matter that one of them's negative, one of them's positive. Okay, the last thing I want to show is that if you put in, so let me put in A and B first. Go from A to B. This code actually works, but the problem is it's really, really slow, and it starts getting very, very slow as the number of points in each one of your sets gets big. So this would give you the same as this guy. So this and these are the same. And if I changed it and I went from B to A, we better get the same thing that we got last time. And we did. We get a 3 by 2. And this one would also be a 3 by 2 with exactly the same numbers. Okay. That's all I have. If you had 3 dimension, if you had 3 data points, again, if you're taking it from that column perspective, you're gonna be fine. You would just have 3 numbers in each one of these instead of just 2. I'm sorry, you would have 3 of these matrices. That's what you would have. So in other words, when you get, let me pull up D again, and I go from the column perspective, I would have 1. So right now I only have 2 matrices. I have delta x, that one's delta y, but then I would have another, I would have a 2 that I could go to as well, and I could see it. So that would be delta z. If you had 4 points, a coordinate system that had 4 points in it, then you would have a 4th one, and so on and so forth. So you could go n-dimensional in that as well. All right, I hope everybody got something out of that. Make sure you use this in your algorithms for your k-means clustering.